In this topic, we look at enabling comparisons that determine cause and effect. And to do this, we look at the pearl millet growth in the Sahel case study. Now, as always, this case study is given in more detail back in topic 1, but as a brief overview, as a little reminder, this is a case study which is an experiment that is designed to investigate the factors that influence yield of millet in order to provide farmers with recommendations on how to optimize that yield. What does this mean? Well, let's say that we were looking at a yield and we want to know which fertilizer results in a higher yield. We then might run an experiment where for half of our crops, we apply fertilizer A, and for half of our crops, we apply fertilizer B. And at the end, we look at the results, we look at our yield for fertilizer A, and we look at our yield for fertilizer B. And we see from this, okay, well, it looks like the fertilizer A resulted in a higher yield than fertilizer B. And this is what we mean by enabling comparisons that determine cause and effect. Here, the comparison is in our fertilizer A versus fertilizer B. And here we have an experiment. We are comparing the outcome in our crop yield between fertilizer A and fertilizer B. And having a treatment and having a comparison like this is what helps us see cause and effect. It helps us decide or determine what things are optimizing our yield. And in the pearl millet growth example, they actually had 4 different treatments that they were looking at. So they had their millet crop residues, which had 3 levels, their phosphorus broadcast, which had 2 levels, 4 different types of genotypes, and then they had a 4th factor, which changed depending on what the year was. To examine these effects, a factorial design approach was used, which allowed for the researchers to examine all combination of the factors. And this gave you 48 treatments. And if you don't believe me, here is, so if we have 3 lots of crop residues and 2 lots of broadcasts and 4 lots of genotypes and 2 lots of the 4th factor, then we have 3 times 2 times 4 times 2, which gives us 48. And if you still don't believe me, then here's a table which is split into 2. So this second half here is the second half of the kind of first table. So we'll just focus on this bit here, where we have our treatment number, which goes all the way from 1 down to 21, from 22 down to 48. We have our crop residues, where we have our 3 different types of crop, S1, S2, and A2. We have our phosphorus broadcast of our 2 levels there of 0 and 13. We have our 4 different genotypes, SL, CIVT, IMVT 5001, and V4. And then we have our 4th factor, which was always 2 levels, but the kind of specifics on what those 2 levels were changed each year, so we've just called them 1 and 2. And overall, that's given us 48 treatment combinations. There shouldn't be an error in there. But if you do find one, then let us know. But I'm pretty confident that all these 48 combinations are unique. At least there's definitely meant to be 48 combinations. So here we have treatment 1 is our first combination, and treatment 48 is our final combination. So treatment 1 is our first row, so that's our first combination, down to treatment 48, which is our final combination. One of the benefits of a factorial design is its ability to investigate the interactions between treatments. So, for example, let's look at treatment 1 to 8. Well, in treatment 1 to 8, crop residue and phosphorus broadcast are constant, right? They do not change. So between treatment 1 and 8, then our crop residue and our phosphorus broadcast, the changes that are the changes in the yield, in the crop yield that are seen when you compare treatment 1, 2, 3, 4, 5, 6, 7, and 8 should not or will not be to do with crop residue or phosphorus broadcast, because we always apply the same level of them. However, the genotypes change and the fourth factor changes. So if we just compare treatment 1 and 2, then we can see how that fourth factor changes for the first genotype, for genotype SL. If we wanted to compare treatment 1, 2, 3, and 4, we can see, okay, how does the fourth factor, how does the first level of that work for SL? How does the first level of that work for CIVT? Is the first level of the fourth factor, does that result in a higher yield under SL than the second level of our fourth factor? But maybe it doesn't for CIVT. And so we can use these combinations of our 48 treatments to help see these different interaction effects as well as everything else. So this is an example of an experiment. An experiment is when we have a treatment, or in this case, 48 treatment combinations. We have an intervention or a treatment which enables the researchers to determine cause and effect on the yield. Thank you.